Welcome viewers to the second segment of the fifth lecture for the online series of lectures for the course of Algebraic Topology 1. In the previous segment, towards the end, we stated Lemma 2 and proved it. It was about the continuous map H from S1 to a given topological space X. And there were a bunch of equivalent statements. The first being H is null homotopic. The second being H having a continuous extension from the unit pole to the given topological space X. And the third property related to H was that H star, the induced homomorphism corresponding to the continuous map H, being a trivial group homomorphism. H star is the trivial homomorphism of fundamental groups. Okay, so we stated and proved this lemma in the previous segment. Now we have a corollary to this lemma, to this second lemma. Let me state the corollary, then I'll prove it. Corollary to lemma 2, which states that the inclusion map J from the unit circle to this topological space, the punctured two-dimensional Euclidean plane, is not null homotopic. Okay, so here goes the proof of this corollary. So there is a retraction of this punctured plane onto the unit circle given by R of X is equal to X over the norm of X. Okay, so one can immediately check that it's indeed a retraction. Then by lemma 1, the induced homomorphism induced group homomorphism J star from the fundamental group of the unit circle with reference to this distinguished point B0 to the fundamental group of this punctured plane is injective. Okay, Now, we invoke this lemma 2. Now, according to this lemma 2, one knows that if this inclusion map is if the inclusion map J is null homotopic, meaning that for this inclusion map 1 holds, okay, then 3 will also hold. Then it will imply that the induced homomorphism J star from the fundamental group of the unit circle with respect to B0 to the fundamental group of this punctured plane okay, this induced homomorphism is trivial, right? Is trivial. So if the inclusion map the inclusion map J is null homotopic, then the induced homomorphism J star is going to be a trivial homomorphism. Okay. Now the point is that we have seen that J star, we have seen that the induced homomorphism J star is injective, okay, which followed from lemma 1. So J star being a map from pi 1 S1 comma B0 to pi 1 the punctured plane comma B0 is injective, and since the fundamental group of S1 with reference to this base point B0 is non-trivial, okay, J star cannot be a trivial homomorphism. So let me write it. Since J star is injective and this fundamental group of S1 with reference to the base point B0 is non-trivial, J star can't be a trivial homomorphism. To phrase it in a different way, the image of J star can't be just the identity group element. Of this group of pi 1 of this punctured plane with reference to this base point B0. Okay, so we we thus see that J star cannot be trivial. So by using the contrapositive version of this statement, so we are going to negate this statement appearing on the right hand side. J star is non-trivial, which means that the inclusion map J cannot be null homotopic. Hence, the contrapositive version of lemma 2 tells us that J can't be null homotopic. Okay, so that was one part. Now for the identity map. Okay, so we are given this identity map I from this pointed topological space S1, B0 to itself. Okay, and from lecture 2, we know that the induced homomorphism corresponding to this identity map is just the identity homomorphism on the respective fundamental group. Okay. So the induced homomorphism corresponding to this identity homomorphism is precisely the identity group homomorphism. Group homomorphism of the fundamental group pi 1 S1, B0 to itself. That we know from lecture 2. Okay, so since it's the identity group homomorphism, it's necessarily injective. Hence, the induced homomorphism is injective, and hence this induced homomorphism is non-trivial, and hence is non-trivial. So again, by lemma 2, then again by the contrapositivity of lemma 2, contrapositive version of lemma 2 confirms that I cannot be null homotopic. Okay. All right. So that's it. The inclusion map of the unit circle onto the punctured plane is not null homotopic. That was one part, and the other part is that the identity map of the circle to itself is not null homotopic. Good. Alright, now we have our third theorem, which is a very important theorem that will be used to prove Brouwer fixed point theorem for the two-disk. So let me state this theorem first and then I'll prove it. Theorem 3. Given a non-vanishing vector field on the unit ball, on the unit ball in dimension 2, there exists a point of the unit circle where a vector field points directly inward, and the point of the circle, of the unit circle, where it points directly outward. Okay, this is what we need to prove. Let's prove it. Alright, so let me recap the notion of a vector field on the unit ball in dimension 2. A vector field on B2 is an ordered pair. Okay? X comma Vx, the first component of this ordered pair gives the base point of the vector field, and the second component gives the vector attached to that base point. Okay, where X is a point on the unit ball in dimension 2, and V is a two-dimensional vector, and V is a map from B2 to R2, and we want this map to be continuous. V is a continuous map, so that V of X is in R2. Okay, so this ordered pair, so the vector field is given by this ordered pair. Okay, to say that a vector field is non-vanishing, means that the value of the vector at X is nowhere this zero, nowhere this origin of R2. Okay, it holds for all X in B2. Okay, it's nowhere 0. Okay, in such a case, if the value of Vx is nowhere 0, 0, then V is actually given by this map, right? V is not just from B2 to R2. To refine it, if V is also non-vanishing, then V is actually a continuous map from B2 to R2 set minus the origin. Okay, which means that this V is a continuous map from B2 to the punctured two-dimensional Euclidean plane. Okay, good. So we'll be concerned with ordered pair where x comma vx, where x is a point on the two-dimensional disk and vx is vx is in R2 set minus 0 comma 0, where v is a map from B2 to the punctured plane, punctured two-dimensional plane, Euclidean plane. Okay. Okay, so we'll prove it by contradiction. So we suppose that Vx does not point directly inward at any point. We suppose that Vx doesn't point directly inward at any point x in S1. Okay, we suppose the contrary. The contrary holds. Okay, now consider the map V from B2 to this punctured plane. Okay, so denote by W the restriction of V to S1. That means that V restricted to S1 is denoted by W. Okay, let me erase this part. In other words, W from S1 to the punctured two-dimensional plane has a continuous extension given by V, right? Which is a map from B2 to the B2 to the two-dimensional puncture plane. Okay. So now so if this is the case, because W has a continuous extension, we can apply lemma 2 to this map W. Apply lemma 2 to the map, to the continuous map W from S1 to the punctured plane. And see that and find that W is null homotopic. Okay. Okay, good. So we have proved that W is null homotopic. Now, observe that W, which is a map from S1 to the punctured plane, is homotopic to the inclusion map J of the unit circle into the punctured plane. So we claim that the homotopy being given by the homotopy from the map W to the inclusion map J being given by F from S1 cross I to the punctured plane F of x comma t is equal to t times j of x plus 1 minus t. It's the straight line homotopy between these two maps. Okay, for all x in S1. Okay, let me erase this bottom part. This is what we need to prove. So in other words, we need to prove that this guy is equal to t times x. The j of x is just x, right? J is the standard inclusion map of the unit circle into the punctured plane plus 1 minus t times w of x, and it should hold for all x in S1. Okay. So one can easily check that, it's a homotopy between these two maps. Okay, so let me draw a picture for you. So suppose we have this unit circle. Okay, this is the unit circle. We choose points, right? 3 points here. Okay, so now see that the inclusion map should point in the direction of outward normal, right? So if this is the center, the outward normal is in this direction. So these are the directions of j sub x. Okay, so this is j of x, sorry, not j sub x, it's j of x. So this point is y, this point is x, and this point is z. Okay, so that so this vector is the w of y comma j of y, and this is z comma j of z, and this is x comma j of x. Okay, and suppose we have some non-vanishing vector field W. Okay, sorry. So the non-vanishing vector field was V, whose restriction to S1 was W. So suppose that this W is like here, is directed this way, and the W here is directed, so suppose here, this way, and the W here is directed this way. Okay, so this point is going to be Y. They are both based at the point Y, and this is Y comma W of Y. That's the ordered pair, and this ordered pair, this vector stands for this ordered pair, X comma W of X, and this vector represents this ordered pair, Z comma W of Z. Okay, so now we immediately see that we can join these two vectors by a straight line. Okay, and and along this straight line, the tail of these two vectors are transforms into each other along this straight line. So these are vectors whose tips belong to that straight line. Similarly here, so you can continuously take this vector Wx into that vector Jx. Okay, similarly you can join the two tips of these two vectors in R2 and continuously take one vector into the other vector lying on that straight line. Okay, good. So this is the picture demonstrating that, demonstrating the homotopy between these two vector fields, W and and corresponding the inclusion map J. Okay, so W is a homotopic to J, where F is a homotopy between them. But we haven't yet shown that f of xt is non-zero, right? That this guy is non-zero. So we expect f to be a map from S1 cross I to this punctured plane, so that f of x comma t cannot be equal to 0, 0. We haven't shown it yet. So let's see how it follows from the fact that W of x, okay, see that W is a map from S1 to the punctured plane into dimension 2, and so is J. J is the inclusion map of the unit circle into the two-dimensional punctured plane. So J of x and W of x are never equal to 0, 0, 0, 0. So W of x is never equal to 0, 0, and J of x is never equal to 0, 0. So from these two facts, it immediately follows that f of x comma 1, if you plug in 1 here, then you just end up with j of x here, right? Because this cancels out. This goes away. So this is simply j of x. So f of x1, x comma 1 is not equal to 0 comma 0. And similarly for f of x comma 0, if you plug in 0 here, then this goes away and you just have w of x. And this is also not equal to 0 comma 0. Okay. So we are done with the two extremes. Now we have to take t. So we have to take intermediate values of t in the unit interval. Okay, so we are done with the two ends of the unit interval. So I need some space. Let me erase this. Suppose if f of x comma t is equal to 0 comma 0 for some t with t lying between 0 and 1, then so we have this relation, right? f of x comma t is equal to this. So if f of x comma t is equal to 0, okay, so then it follows that this guy is 0, right? Tx plus, so for simplicity, just write it as 0, okay? T times x plus 1 minus t times w of x is equal to 0. So if this is the situation, then it turns out that w of x is equal to minus t over 1 minus t times x. So this guy is positive because t lies between 0 and 1. T is, positive, of course, because t is greater than 0. So definitely wx is a negative scalar multiple of x. That is, w of x equals a negative scalar multiple of x. Okay, good. So we have found that w of x is a negative scalar multiple. It geometrically means that w of x points directly inward at x belonging to S1. Okay, because the outward direction is designated by the positive sign. Okay, so since this is negative, it turns out that w of x points inward, directly inward. It geometrically means that w of x points directly inward at x in S1. Contradiction. Because we assume that there is no such point, right, where the vector field points directly inward. Hence, f of x comma 2 t is not equal to 0, 0 for all t in the unit interval, closed unit interval. Okay. We first prove that this f is non-vanishing at the two endpoints of the unit interval. Later we prove that for the intermediate points as well, this guy f cannot be 0. Okay. And this map f from S1 cross I to the punctured two-dimensional plane is the required homotopy between the map W and the map J. Okay? Right. So we proved earlier that W is null homotopic using lemma 2, right? We proved earlier that W is null homotopic. Okay, and now we have proved that W is homotopic to J, and so J is null homotopic. So J is null homotopic. Okay, but in corollary to lemma 2, which we proved at the start of this segment, okay, we proved that this inclusion map of the unit circle into the punctured plane okay, we proved that this is not null homotopic. Okay, which contradicts our finding that J is null homotopic. Hence, this is how we reach a contradiction, and hence there must be a point. Hence, there must be a point X in S1 where B of X points directly inward. Okay. Okay. All right. Now about the existence of the point where the vector points directly outward. Okay. Now if we have studied Now the proof with the vector field x comma minus g of x instead of x comma d of x, and carried out the arguments as before. We would have reached the conclusion that minus v of x points directly inward. So whatever we carried out with v of x now will be translated to minus v of x, right? So we found earlier that v of x points directly inward. Now the conclusion would be that minus v of x points directly inward using the same argument. At some point x in S1. Okay, or in other words, so we have to translate what we have found in terms of our original vector field x comma v of x, right? Because we cannot change the vector field. So the conclusion that we reached here is with reference to this vector field. But if you want to translate this conclusion using our original vector field, it turns out that there is a point x in S1 for which the vector v of x associated with the vector field x comma v of x points directly outward. Right? Well, minus v of x pointing inward is equivalent to saying that v of x points directly outward. Okay, so which means that there exists a point x in S1 for which a v of x would point directly outward. Okay, so thus we have proved that there exists a point where the vector field points directly inward, and there also exists a point where the vector field points directly outward, corresponding to a given point x on the unit circle. Okay, so this is what we need to show. QED. Okay, so now it's time to state the Brouwer fixed point theorem and prove it. So at this point I'll take a short break and we'll be back with the discussion on Brouwer fixed point theorem for the 2 disc. Thank you for attending this second segment.